The Konkan Railway runs through a corridor that receives more than 3 meters of monsoon rain in 4 months. Between 1990 and 1998, engineers laid 760 kilometers of track across terrain that liquefies, collapses, and moves during every rainy season. The question was never whether to build through monsoon country. The question was how to anchor a railway to ground that refuses to stay still. India's west coast had been a transportation gap for more than a century. The Western Ghats mountain range rises abruptly from the Arabian Sea, isolating the Konkan region between Maharashtra and Goa from the inland plateau. Ratnagiri, roughly 90 kilometers north of Goa and 250 kilometers south of Mumbai, sat on the Arabian Sea coast with no direct rail link to either city. Travelers relied on a single coastal highway, National Highway 66, or detoured hundreds of kilometers inland through older rail routes that swung east around the mountains. The detour added entire days to journeys that looked short on a map. In 1984, the Indian government approved a direct coastal railway. The promise was simple: connect Mumbai to Mangalore, cutting travel time and opening the Konkan region to industrial development. The engineering brief was not simple at all. The Konkan Railway Corporation began surveying in 1990. The route required 2,000 bridges and 92 tunnels through fractured basalt and laterite soil. Laterite is iron-rich clay that hardens when dry and turns to slurry when saturated. During monsoon season, the Western Ghats receive between 2,500 and 4,000 millimeters of rain. That volume does not drain gradually. It arrives in concentrated bursts that overwhelm the soil's load-bearing capacity within hours. Engineers were not designing for stable ground interrupted by occasional flooding. They were designing for ground that changes state every year. The challenge extended beyond the slopes themselves. Every bridge foundation had to account for rivers that could rise several meters in a single night. Every tunnel portal had to resist water pressure from saturated rock masses above. The geology was not hostile by accident. It was shaped by millions of years of seasonal inundation, and it would not cooperate with a static structure. The first approach followed standard practice for mountainous railways. Design teams specified deep-cut excavations for track beds, with drainage channels to carry runoff away from embankments. Early test sections used conventional ballasted track, crushed stone supporting wooden or concrete sleepers. The 1991 monsoon demonstrated the problem. Entire sections of prepared roadbed slid down slope as rainwater saturated the laterite substrate. Drainage channels could not evacuate water faster than the soil absorbed it. The subgrade was not failing because of surface water. It was failing because the soil itself was becoming a fluid mass several meters deep. Conventional embankments rely on the soil beneath them remaining solid. When that assumption breaks, the embankment does not settle gradually. It moves laterally, shearing off its foundation and carrying the track structure with it. Engineers measured displacement of up to 2 meters in some sections during a single monsoon event. Repairing the damage after each season would cost more than the original construction, and the line would spend months out of service every year. The turning point came in 1992, when the engineering team shifted focus from drainage alone to soil stabilization. Standard solutions like cement grouting and retaining walls could not address the scale of the problem. Grouting individual slopes would require years and exceed the project budget. Concrete retaining walls would crack under differential settlement as the saturated soil moved at different rates along their length. The corporation brought in geotechnical specialists who proposed a hybrid approach: accept that the soil will saturate, but prevent it from moving. That meant anchoring the railway not to the surface layer, but to the stable rock beneath it. The laterite might liquefy, but the basalt underneath was solid. If the track could be tied to that deeper layer, surface instability would not matter. The solution combined three elements. First, soil nailing. Steel rods up to 12 meters long were driven through the laterite into the underlying basalt at intervals along every unstable slope. The rods were grouted in place, creating a reinforced soil mass that could deform slightly without losing cohesion. The nails did not stop the soil from saturating. They stopped it from sliding as a coherent block. Second, gabion walls. Wire mesh baskets filled with stone were stacked along the toe of slopes to provide flexible, permeable support that would not crack under differential settlement. Unlike concrete, gabions could deform with the ground and still maintain their structural function. Water passed through them, rather than building up hydrostatic pressure behind them. Third, bioengineering. Fast-growing native grasses and shrubs with deep root systems were planted on stabilized slopes. The roots formed a biological mesh that reduced surface erosion and improved water infiltration without adding rigid weight. The vegetation also transpired water during dry months, reducing the moisture content in the upper soil layers before the next monsoon arrived. None of these techniques were new individually. Their coordinated application across hundreds of kilometers of continuous unstable terrain was unprecedented in Indian railway construction. The cost of soil stabilization added approximately 18% to the original construction estimate. The Konkan Railway Corporation reported total project expenditure of 36 billion rupees, equivalent to roughly $1.1 billion at 1998 exchange rates. Soil nailing alone accounted for more than 2,000 kilometers of installed anchors across 63 landslide-prone zones. Critics argued the expense was excessive for a regional railway serving a relatively sparse population along the coast. Supporters pointed to the alternative, a line that would require continuous emergency repairs and seasonal closures, negating the economic justification for building it at all. The debate reflected a broader tension in infrastructure planning. Standard cost-benefit analysis compares construction expense to projected revenue. It rarely accounts for the cost of not building or the compounding expense of building inadequately and repairing forever. Construction proceeded in parallel across multiple sections to compress the timeline. Conventional railways are built sequentially to allow testing and adjustment. The Konkan project used a segmented approach, with separate teams working simultaneously on different mountain passes and river crossings. That strategy introduced risk. Design errors could not be corrected before replication across other sections. In 1994, a tunnel collapse near Ratnagiri killed 8 workers when monsoon water infiltrated a partially lined bore. The investigation found that the rock mass had been more fractured than seismic surveys indicated, and the support system had not been adjusted before excavation advanced. After that incident, the corporation mandated real-time geological logging in every active tunnel and required engineer approval before blasting each new face. The change slowed tunnel progress by roughly 15%, but eliminated further collapses during construction. The trade-off was accepted because the schedule could absorb modest delays, but not fatalities or the regulatory shutdowns that would follow them. The railway opened to freight traffic in March 1998 and to passenger service in May of the same year. It reduced travel time between Mumbai and Mangalore from more than 24 hours to under 12. By 2005, The line was carrying 15 million passengers annually and moving significant volumes of containerized freight from inland India to West Coast ports. Chiplun, once a highway town with no rail access, became a commercial hub with direct connections to Mumbai and Goa. The soil stabilization systems have required ongoing maintenance. Sections of gabion wall are rebuilt every 5 to 7 years as wire mesh corrodes in the humid coastal air. Soil nails are inspected annually and replaced when corrosion reduces their load capacity below design thresholds. The maintenance cost is predictable and manageable, a planned operational expense rather than an emergency repair cycle. That distinction matters. Planned maintenance can be scheduled around traffic. Emergency repairs shut down revenue and strand passengers. The Konkan Railway demonstrated that building through monsoon terrain is possible, but only by designing for movement rather than rigidity. Engineers did not eliminate landslides. They anchored the railway deep enough that surface instability could not dislodge the track structure. The technique has since been applied to highway projects in India's northeast and mountain railways in Nepal, where seasonal rainfall creates similar ground conditions. The lesson is not about defeating the monsoon. It is about accepting that some environments cannot be made stable, only managed continuously. The Konkan Railway still operates through the same saturated slopes and fractured rock that made construction so difficult. The difference is that the infrastructure was designed from the beginning to coexist with that instability, rather than assuming it could be engineered away. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.